So today we're going to be having a look at derivatives of exponential functions using both the product rule and the quotient rule. So let's start off with a function. Let's do f of x is equal to x to the 3 e to the negative 2x. Okie dokie. Now this is a perfect case for using product rule. Why? Because I have two functions being multiplied together, and that's what a product rule is. So to remind myself, if I have a function f of x is equal to uv, well then f dash of x is going to be the derivative of u times v plus the derivative of v times u. Slightly different version on your formula sheet, but they're all the same thing in the end. So in this case, well, we just need to work out what u and v are. So u is equal to x to the 3, v is equal to e to the negative 2x. Derivative of u dash, is just going to be 3x squared. Using the power rule, v dash is going to be e to the negative 2x because the derivative of e to the x is e to the x, but chain rule multiplied by the derivative of minus 2x, and the derivative of minus 2x is just minus 2. So simplifying that, v dash we're going to use is negative 2 e to the negative 2x. Alrighty, so now we can just substitute into the product rule formula. So f dash of x is going to be equal to u dash v plus v dash u. Doing our substitution, f dash of x is going to be equal to 3x squared multiplied by e to the negative 2x plus minus 2e to the negative 2x times x to the 3. Alrighty. So now we've got to do a little bit more multiplication, but it's actually not going to be too bad. If we have a look at these multiplicative items, none of them are going to be combinable. So we're just going to get 3x squared e to the negative 2x. And similarly over here, we're going to get negative 2x to the 3 e to the negative 2x. The only reason I'm writing the negative x to the 3 before the e to that is that I'm trying to be consistent with the terms over here, writing the x part before the e to the x part. You could write it in the opposite order, but generally speaking, we're usually going to put constants, then we're going to be putting power terms, and then we're going to be putting other functions. It's just convention, not a huge deal. Alrighty, so that's just product rule. And realistically, if you're good at product rule, it is just a bunch of little derivatives and then a bunch of multiplication and addition. That's it. Oh, the only thing we might want to write this instead is minus 2 instead of plus minus, but it doesn't actually matter. Alrighty, let's do a quotient one. So imagine instead we had y is equal to let's say e to the 3x plus 1 over, and let's put this over e to the negative x, something like this. Alrighty, well, as a reminder, if y was equal to u over v, then dy dx would be equal to u dash v minus v dash u all over v squared. Alrighty, so we've just got to apply it. The top is going to be our u, the bottom is going to be our v, and we can go. So u is equal to e to the 3x plus 1 let's just call it u dash. What am I doing? U dash is equal to e to the 3x times 3, right? Because remember, chain rule, always got to do chain rule. What's the derivative of 1? The derivative of 1 is 0. Even if it's next to an exponential, the derivative of constants is still going to be 0. So in this case, the derivative just becomes 3e to the 3x. Okay? The derivative of 1 is 0. Alrighty, let's deal with v now. V is equal to e to the negative x. V dash, chain rule, is going to be e to the negative x times negative 1, or negative e to the negative x. Alrighty, so I've got our 4 bits. Now I can work out dy dx. And dy dx is going to be u dash v minus v dash u over v squared. Or derivative of top times bottom minus derivative of bottom times top, all over bottom squared. Alrighty. Going to be a little bit of algebra involved in this next step. So apologies for those of you who don't like a bit of algebra. But u dash was 3e to the 3x, e to the negative x for v, minus v dash, which was minus e to the minus x. U is equal to e to the 3x plus 1, all over v squared, which is just the bottom term, so that's e to the negative x squared. Alrighty, we're going to do a bit of algebra on this, so I'm going to move it to the next page. Alrighty, so let's deal with this a little bit at a time. So the first thing, let's look at this little section here. So we're going to get 3 times e. Now this can actually be a little bit combined, and we'll look at how in a moment, but for the moment let's just write it without the brackets. So 3e to the 3x, e to the negative x. Remember, expanding brackets, we don't have to worry too much. Why? Because, again, this is multiplication, not addition. Everything is multiplication. Minus. Now, we've got a minus minus, so that's just going to become a plus. Oh, sorry. We're looking at this. It's going to be minus minus, which is going to become a plus. But we are going to have to expand out these brackets. So I'm actually going to leave the minus for the moment, and instead expand this out. Why is this one expanding brackets properly? Because there is an addition sign happening right over here. So let's expand these brackets out. So we're going to get minus e to the minus x times e to the 3x plus minus e to the minus x times 1. Alrighty, and this is going to be all over. Okay, well, this bottom part down here, let's have a think. We actually have an index law that deals with brackets of powers, and the answer is multiplication. So we're going to get e to the minus x times 2, or minus 2x. Okay, now let's start dealing with the top. And speaking of index laws, we've got a lot of index laws that are going to be useful here. First index law, let's look at here. These are both under the same power, so both power of e. Multiplication means addition, so we're going to get 3e to the 3x minus x, or plus minus x, right? And that's just 2x. Alrighty, looking over here, we've got a similar situation. In fact, pretty much the same situation. So minus e to the minus x plus 3x, which once again is equal to 2x. Over here, we've just got times by 1 means we're just going to get the original thing, so minus e to the minus x. And all over, the denominator is actually pretty much finished, so e to the negative 2x. Now, carrying on for a little bit more, we can then clean it up a little bit further. So dy dx equals 3e to the 2x minus, well, let's get rid of this minus, so let's expand the brackets. These are both going to become positive terms, so e to the 2x plus e to the minus x, all over e to the negative 2x. Now just check for like terms up on the top, and you can see that we actually do have 2 like terms. These are both e to the 2x terms. They can be added together, and we'd be left with 4e to the 2x, because we had 3 plus 1, so that's 4. And the last thing that we might choose to do, it's an option, but it's something that we might choose to do, is actually get rid of this negative index on the bottom by moving it to the top. Got to be careful though. This is a perfectly fine answer. I'm going to go one step further. There's 2 ways we could do it. One is we could expand it. The other is doing direct division. I'm going to go with the direct division route. which means I could split this out to look like 4e to the 2x over e to the negative 2x plus e to the negative x over e to the negative 2x. Now, which law can we use here? Well, this is division of things with the same base, meaning the e's are the same base. So it's going to become subtraction. So we're going to get 4e to the 2x minus negative 2x, which becomes plus 2x, which is 4x, plus, and then over here we're going to get x to the minus x minus minus 2x. Once again, subtract them. And in this case, minus minus becomes positive, so this is just e to the x. And so we get, as the final answer to what was the derivative of that original function, is actually just 4e to the 4x plus e to the x. Alrighty, bit of a long one, but the main core of the idea is just what we did on the first page. This was just algebraic nonsense, and especially reminding you of your index laws and how we always need to be able to apply them. Alrighty, see you in the next one. Bye-bye.